Welcome to today's class. We're going to be starting with chapter 5 today, but before we do that, I'd like to take the time to do a warm up off of section 4, off of chapter 4. So, if you would try this problem and then take a look at the answers to this one. Okay, on this one, as you can see, you're told that the probability for a positive is 0.025. You're going to take 10 random samples, and you're asked to find the probability that the combined sample will reveal a positive result. So this is one of those composite tests that we've talked about. So in order for the combined sample to test positive, at least one has to test positive. So the probability of at least one is 1 minus the probability of no positives. And just remember this and this always need to correspond here. Okay, and then once you do the rewriting, it may not correspond anymore. But so you've got 1 minus the probability that they're then all negative. So all negative is the same as no positives. So 1 minus the probability that they're all negative would be 0.975 to the 10th, and you get this as your probability. So is that probability low enough so that further testing of the individual samples is rarely necessary? In order for that to be true, it would need to be less than 0.05. We're at about 22.5%. So about 22% of the time, we would need to further test. So it is not low enough for us to say that it's rare for us to have to test further in this situation. Okay, like I said, today we're going to move on into chapter 5. And in chapter 5, we're going to be talking about probability distributions. And specifically, we're going to look at binomial probability distributions. So today we'll cover section 5.1 on probability distributions. We're going to be looking at just generic probability distributions, the characteristics of those, and how to find the mean, variance, and standard deviation of the probability distributions. The next class we'll look at binomial probability distributions, and then we're actually not going to do section 5.3 on the Poisson probability distributions. Okay, so the first definition that I want you to be familiar with is that of a random variable. So a random variable is a variable, typically denoted by x, that has a single numerical value determined by chance for each outcome of a procedure. So your random variable might, for instance, be the number of girls out of 5 births. It might be the number of heads out of flipping a coin 10 times. It might be the number of people that have blue eyes out of a sample of 25. So those are some different examples of a random variable. They're basically your outcomes, the potential outcomes for a particular procedure. They do need to be numerical. So our outcomes couldn't be something like Democrat, Republican, and Independent. They need to be numerical in nature. Okay, so a probability distribution is a description that gives the probability for each value of the random variable. So just like we were saying there, your random variable is going to be a list of the possible outcomes. Then the probability distribution is going to assign a probability to each of those outcomes. So like we were saying, in a group of 5 births, what's the probability of getting no girls? What's the probability of getting 1 girl, of getting 2 girls, getting 3 girls, of getting 4 girls, or of getting all 5 girls? And so that is going to make up our probability distribution. When we combine all that together, it can be expressed in a couple different ways. We can express it as a table, as a formula, or even as a graph. Okay, in this chapter, we're going to specifically look at discrete random variables. In chapter 6, we'll look at continuous random variables and the difference. So a discrete random variable has a collection of values that's either finite or countable. If there are infinitely many values, the number of values is countable if it's possible to count them individually, such as the number of tosses of a coin before getting heads. So we might have to go a long ways before we get heads, but we may not know exactly when that's going to be, but it is possible to count them individually as we go. So this goes back to chapter 1, where we talked about discrete being things we can count, continuous being more measurable with infinitely many possible values. Okay, so here's a definition for continuous random variable. It has infinitely many values, and the collection of values is not countable, so it's impossible to count the individual items because at least some of them are on a continuous scale, such as body temperatures. So that's why measurement is typically continuous, because there's infinitely many possible outcomes that we can have from that. So if you're measuring body temperature, depending on how accurate your instrument of measurement is, there's infinitely many possible values you could get from that. And so we wouldn't count somebody's temperature, we would measure it, and we would get the potential for infinitely many values. Okay, so this is just a chart kind of showing the breakdown here. With random variables, we can either look at them as discrete in chapter 5 or as continuous in chapter 6. In chapter 5, they're either finite or countable as far as the number of values. They can be listed, and an example of this would be a binomial distribution. In chapter 6, they have infinitely many values, so we are not able to list them. It's associated with a continuous scale without gaps. And the probability distribution that we're going to look most at there are the normal probability distributions. Okay, so the requirements for a probability distribution, there are 3 of these, and you need to know these. The first is that you have to have a numerical random variable. So just like I mentioned earlier, your random variable x needs to be a number. It can't be like, the eye color of someone or something like that. It's got to be an actual number and of an outcome that you could have. The second one, the sum, this is the Greek symbol for summation. So the sum of your probabilities for the distribution has to equal 1. I have an asterisk by it because if you get something like 0.9999 on your calculator, then that's probably going to be 1. It's just due to rounding, it's not coming out exactly 1. Or if you get something like 1.00001, again, due to rounding, that's essentially 1. It's just not coming out 1 on the calculator. So 1 or something of this nature is sufficient for this one. The third is true for all probability, but your probabilities all have to be between 0 and 1. Okay, so this is an example of a probability distribution that you might see that's represented as a table. This one we're tossing 2 coins, and the random variable is going to be defined to be the number of heads when 2 coins are tossed. So this one's discrete because we're able to list the possible number of heads. So if we're tossing a coin twice, we might either get 0 heads, we might get 1 head, or we might get 2 heads. When we assign the probabilities to those, you will see that you'll get this as your probability distribution. Looking at this, just to verify, your random variables are all numeric. Each one of these are between 0 and 1. And if we were to add these up, they add up to 1. So it does fulfill all 3 requirements for being a probability distribution. Probability distributions can be represented as a probability histogram, and it's very much like a relative frequency histogram, except you have a probability here on your vertical axis. And if you look at this, if you added them all up, they're all going to add up to 1. If you're adding the heights of the bars, they're all between 0 and 1, and the number of heads is numeric in value. You can also use a probability distribution. You can construct one using the formula. I'm going to hold off on doing this until a little bit later when we look at the binomial distribution, but a formula is a way that we could represent this. Okay, here's a probability distribution. If you're asked to determine if it, it may or may not be a probability distribution. You're asked to determine if it is one. So if we look at this, first of all, your x should be numbers. So that's the first place that it's going to fail, is that your random variable is not numeric. The second place it's going to fail is that these add up to something besides 1. Okay, the third one, it actually passes, but that's not enough. It needs to be true for all 3. And so it does pass the third one that says they all have to be between 0 and 1, but it fails on the first characteristic and the third. Sorry, and the second. The first and the second. Okay, one thing to mention here, we're going to be finding the mean, standard deviation, and variance. These are parameters because we're actually talking about the entire population instead of a sample. So when we talk about mean, we're going to use the symbol mu in this chapter. Variance is going to be sigma squared, and standard deviation is going to be sigma. So we'll be using these symbols instead of x bar, s squared, and s. Okay, here's our formulas that we're going to be using to find the mean. So the mean mu for a probability distribution is the sum of the product of the x times p of x's. So find all your random variables times their probabilities and add them all up, and that gives you the mean. The variance, we have two formulas for this. The variance itself is a measure of how far the values are from the mean. And that's why you see the value having the mean subtracted from it and then standardized. That conceptually, that's an easier formula to understand. This last one here is an easier formula to actually use. So to do this one, we'll take our random variable and we'll square it. We'll multiply it to the probability, and then we're going to add all of them up. And then the last thing we're going to do is subtract the mean squared from it. So these are on your formula sheet. There's no need to memorize them, but you do need to understand them and know what to do with them. Okay, anytime we have our variance, we can simply go to the standard deviation by taking the square root of all that. So this is not really a new formula, it's just taking the square root of this one we just saw here. Okay, expected value is actually another word for the mean. So basically it's saying if we were to repeat the procedure over and over and over again, what would the mean value or the expected value be of a particular probability distribution? All right, so we're back here to the one that we looked at earlier that we checked to make sure it satisfied the requirements. We want to find the mean, the variance, and the standard deviation for this distribution. So the first thing we want to think about is the mean formula is the sum of x times p of x. So I'm going to do this with a chart. You do not have to do the chart as long as you understand the notation and can keep it organized. It's not required that you make a chart. To make the chart, what I'm going to do is I'm going to make a column here, and I'm going to put x times p of x, because again, that's what my formula was leading me to need to do, is multiply my random variable and my probability. So if I multiply these two together, this is my x and my p of x. If I multiply these two together, I get 0. Here I get 1 times 0.5 is just 0.5. 2 times 0.25 is 0.5. Okay, so I did this part. I did x times p of x. Now I've got to take care of the summation part. So I'm going to sum these all up, and I'm going to get 1. And that is my mean. Okay, so this would be the mean for this problem. Okay, moving on to finding the variance. The variance, if you recall, is the sum of x squared times p of x, and then we're going to subtract the mean squared from that. So hold on to this value because we're going to have to use that to find the variance. Okay, so looking at this one, we already used this column, so I'm going to actually just be using this column here. So I'm going to square my random variable and then multiply it by the probability. So that's going to give me 0. 1 squared times 0.5 is going to give me 0.5, and 2 squared times 0.5 is going to give me 1. Okay. So again, looking at this formula, okay, I've done this x squared p of x part. So the next thing I need to take care of is the summation. So to do the summation, I need to add all of these up. So when I add them all up, I get 1.5. That is not the variance. The number one mistake I see people make is to tell me that's the variance. It's not the variance yet. We've only done this part. We've still got to do this other part over here. So what we have found when we find that is the sum of x squared times p of x. We've not found the variance. So the variance then is going to be this part, which is 1.5 minus my mean. So if I go back a screen here, my mean was 1 squared. Well, 1 squared is just 1. So my variance is going to be 0.5. Since the X represents the number of heads, this is 0 heads, 1 head, 2 heads. Variance is a squared term, so we're going to have, this will be heads squared. Okay, we want to last find our standard deviation. So standard deviation is simply the square root of our variance. So I'm going to take the square root of the 0.5, and I'm going to get 0.707. We typically round these to 1 decimal place in chapter 5, so that's going to be 0.7 as my answer. So that's going to be the variance for this problem. Okay, so as far as interpreting it, the mean just says that if you were to flip a coin twice and do it over and over and over again, the expected value or the mean number of heads when 2 coins are tossed is going to be 1, which means that was what we would expect to get. If you're doing flipping two coins and you do that over and over and over again, on average, you're going to get 1 head per time that you do that activity. So our variance is 0.5 heads squared, standard deviation is 0.7 heads. Okay, you can do these in your calculator. So what I'm going to do is I'm going to jump over to the calculator screen and show you how to put these in your calculator. So the first thing I want you to do is to actually go all the way up here and let's clear everything out in columns 1, 2, 3, and 4. So I had already cleared out L1. If we clear out L2, we'll just do clear, enter, and it'll take everything out. We'll go up and over to L3, clear and enter, and same thing with L4. Okay, so now we're going to go back over to L1, and L1 is going to represent our random variable. So on the table we were just working with, our random variables were 0, 1, and 2. L2 is going to represent our probabilities. Okay, so with L2, the probability of a 0 was 0.25. Probability of 1 was 0.50. And the probability of 2 was 0.25. Okay, now we're going to let the calculator do some of the work for us. And it's not that impressive on this problem because this problem is so small. But if we get a much bigger probability distribution, it can be very helpful. So go all the way up to where L3 is highlighted. And what we want to do, if you recall, L3, or the next column, what we did was we multiplied x times p of x. Well, x is our L1 and p of x is our L2. So we're going to tell it to do L1. So we'll do second and number 1. So L1 times L2. And that's the same thing as x times p of x. Press enter, and then it fills in those same values that we had just calculated on our table. I'm going to go over to L4 now. And if you recall, this next column we did was x squared times p of x. So what I'm going to do is I'm going to do L1 squared, because that represents my x's, and then I'm going to multiply that by L2. Press enter. Okay, and I have those values. So I can easily fill in the values from here, but ultimately we're not really interested in the values as much as the sum of each of the columns. So if I want to sum L3, get the total here, what I'm going to do is I'm going to go to Stat, I'm going to go over to Calculate, I'm going to choose one variable, Stats, and then I'm going to tell it to work with L3. Okay, remember that I wanted the sum of that column. So I'm going to go right here. That's the sum of my column. So the sum of that column is 1. And that's what my mean is going to be for the probability distribution. A lot of people get confused and they're like, oh, this is the mean. This is not the mean that we're looking for, okay? The mean that we're looking for is simply the sum of those values in that column. And that's why we're going to take this value here as the mean for that distribution there. If I want to find the sum of L4, which is going to help me in finding the variance, I'm going to do the same thing, except I'm going to tell the calculator L4 and again, I'm looking for the sum of that, and so the sum of that is 1.5. So these values should be matching up with what you saw on the table that we just finished. So no, your calculator is not going to directly find the mean for you or directly find the variance for you, but it is going to be helpful in organizing the data. So you can see that sum that we just found on the calculator is the same sum we get here and get 1.5. So then to find your variance, you're still going to have to put it in and do the sum of the x squared times p of x minus the mean squared and get your variance and your standard deviation. Okay, so here's another one. I'd like to give you a few minutes to try this one. One thing I want to say about it is that 0 plus is basically, when you see 0 plus, it means it's a very, very small number, something like 0.00000001. We don't put 0, though, as a probability unless it's impossible. So if there's any chance at all for it to happen, even however rare it is, we put 0 plus instead of 0. Having said that, mathematically, when you're multiplying, you will treat it as a 0, as just a normal 0. So give this one a try. First of all, go through the 3 criteria to determine whether it's a probability distribution. And then if it is, go ahead and find its mean, variance, and standard deviation. Okay, so these are the values that you should have gotten when you went through and multiplied. The first column here would be x. Remember, this is x and this is p of x. So multiply those two together and you get this. This column, you're going to do x squared times p of x. So square the first column and multiply it by your probability, and you get this column. So as far as answering the mean, you're going to add all of these up, and when you get them all added up, you're going to see that they add up to 6. So 6 is going to be your mean. For the variance, you're going to add all of these up here, and you're going to get 37.494. Remember, that is not the mean, not the variance. You're going to have to then take that value and subtract the mean squared from it. So we found the mean to be 6. We're going to take that and subtract the mean squared. We get 1.494, or if we round it to 1 decimal place, it would be 1.5. The standard deviation will take the square root, go back to the unrounded one to take the square root, take the square root of it, we get 1.222, and that's going to round to 1.2. One thing I failed to mention, determining whether it is a probability distribution. If we look at this, if we add all these up, it adds up to 1. Everything is between 0 and 1, and these are numeric, so it does satisfy all those requirements. I wanted to go back through this with the calculator one more time, just so we don't have any confusion any further with this. Okay, so here we are over at the edit screen on the graphing calculator. So we put our x's in here, we put our p of x in here, and then for the L3, if you remember, you want to go all the way up here and highlight it and put in L1 times L2. If you're getting error messages, you're probably not going all the way far enough up. You need to have this part highlighted before you type in L1 times L2. You go over here and type in L1 squared times L2, and then it fills these values in for you. So as far as getting the total here, we're going to go to stat calculate, one variable statistics, and we want to find L3 and calculate. Okay, so again, if you recall, this is the mean that we had on that previous table, and this is where the mean or the sum of that column is going to show up. Okay, if we go and look at for L4, Okay, so here's the sum, and that's that same number that we just reported as the sum of that column. And that's not the variance. You still have to subtract from that the mean squared before you're able to use that as your variance. Okay, here's one last one if you feel like you need some further examples. If you don't, go ahead and fast forward through this example and pick up with the next concept. Okay, so this is what you should have gotten for this example here. We've got, if you put this in your calculator, you do L1 times L2. This one would be L1 squared times L2. Add them all up and you get the mean. You want to round that to 1 decimal place, and so you get this answer. Here, if you add them all up, you don't get the variance, but you get a part we're going to use for the variance, so we'll use it here. Subtract the mean squared from it and be sure to round to 1 decimal place. Here, you want to take the square root to get the standard deviation. Take the square root of this unrounded value before you report your answer here. So don't take the square root of the 0.4, take the square root of this answer, and you'll get 0.6. One thing again I failed to mention is checking to make sure it's a probability distribution. All these are between 0 and 1. They add up to 1 or pretty much 1 with some rounding issues, and then all of these are numeric. Okay, we can still use this range rule of thumb to determine if something's significant, is a significant value, if it's significantly low or significantly high. And that still goes back to that mean plus 2 standard deviations. So like looking at the coin example that we started talking about, we found that the mean was 1 and the standard deviation is 0.7. So if we're going to determine if 2 heads is a significantly high number of heads, then we're going to do the mean plus 2 standard deviations. So that's going to be 1 plus 2 times 0.7 or 2.4. So in order for it to be a significantly high number of heads, it'd have to be greater than 2.4. But 2 is not greater than 2.4, so it would not be considered a significantly high number of heads. Okay, so we've talked about this before, but a significantly high number of successes, you're said to have a significantly high number of successes if the probability of X or more successes is 0.05 or less. So basically, if we're looking at these probability distributions, if we're talking about, and I'm just going to kind of write some out here, typically we're not really concerned about, say, the number 8. What we're really concerned about is 8 or more, okay? Or we might not be concerned about the number 2, but we're concerned about 2 or less. So when we're determining if something's significantly high, then we're going to be looking at that number and greater than that. If we're looking to see if something is significantly low, then we're going to be looking at that number or less than that. But in doing that, the probability of any of those situations needs to be less than 0.05 for it to be considered significant or not. Okay. And again, the 0.05 is not absolute. In certain situations, that could be changed, but basically that's what we use in this class. So we already kind of talked about significantly low with that. Okay, and the rare event rule. So basically, if something is, if under a given assumption, the probability of a particular outcome is very small, and the outcome occurs significantly less or significantly greater than what we expect with that assumption, then we conclude that the assumption is probably not correct. So this is kind of the basis for hypothesis testing that we'll get to in Chapter 8. And hopefully, as we keep investigating this rare event rule, it's going to become clearer as we go. Okay, here is an example. It's kind of the same one we did, except here we're not finding the mean, variance, and standard deviation. We're actually answering these questions. I wanted to put it in because you do have one on your homework that's similar to this. So we want to find the probability of getting exactly 3 peas with green pods. So here's 3 peas with green pods. So here's the probability of getting 3 peas with green pods. So that's going to be 0.023. So we're just literally reading it off the table. Find the probability of getting 3 or fewer. So this is where we're talking about 3 or fewer. So we're going to literally add all 4 of these probabilities together, and we said these will just act like 0. So 0 plus this one and this one is going to give me 0.027. Okay, which probability is relevant for determining whether 3 is an unusually low number of peas with green pods? Unusually is kind of the same wording as significantly. They, depending on the version of the textbook, sometimes they interchange these. But basically, going back to what we said earlier, we're not concerned about 3 itself. We're concerned about 3 or fewer in order to determine if something is significantly low. So that's the part B is going to be the one that we're wanting to use to determine if it is an unusually low or significantly low number of peas with green pods. So looking at our probability from part B, this is the one we want to use. In order to determine that, it is less than 0.05. So we would say that it is significantly low or unusually low. Okay, we already mentioned expected value is basically another word for the mean. So I want to do a couple expected value problems to wrap up the section today. Okay, here is an example. 1,000 tickets are sold at $1 each for a color television valued at $350. So I've got this little raffle, maybe a school raffle, church raffle, something like that. What is the expected value of the gain if you purchase one ticket? So if you were to purchase a ticket over and over and over again, how much do you expect to gain or lose if you play this raffle repeatedly? Is kind of what we're investigating here. So what I want you to do is I want you to set up a probability distribution. Okay, you've got your x is going to be your random variable, and you've got your p of x is going to be your probability, and you've got these different scenarios. So let's think about if you were to play this raffle and win, what is your, and I'm going to put net here, what is your net gain? So you paid $1 for your ticket, you won a $350 TV. So what is the net gain there? So if I look at that, my net gain is going to be $350 minus the dollar I paid. So my net gain is going to be $349. Okay. And my net loss, if I were to lose here, is going to be, I'm going to be out my $1. So it's going to be negative. So I'm going to have negative $1. Okay, the probability that I win, there's 1,000 tickets, and we're assuming that there's only one winning ticket, so 1 out of 1,000. The probability that we lose, well, all the other 999 tickets are losing tickets, so 999 out of 1,000. Okay, so from here, once we have this completed, it says what's the expected gain, and we know that the expected gain is the same as the mean. And to find the mean, we do x times p of x. So I'm going to multiply these two together. I'm going to have 349 over 1,000. And then here I'm going to have negative 999 over 1,000. You don't have to keep it in fractions. You could go ahead and convert to decimals, and that's fine. This gives me negative 650 out of 1,000, or if I'd converted at this point, I'm going to get negative 65 cents. Okay. All right, so my expected value or my mean for this scenario is negative 65 cents. In other words, if I play this and buy tickets over and over and over again, then I'm going to average losing about 65 cents for every time that I play this. Okay, this is one that's a little bit more realistic, I think. Definitely probability plays into actuarial science with insurance and so forth. So here we have a 25-year-old woman that pays $245 for a 1-year life insurance policy. and she has coverage of $180,000. If the probability that she will live through the year is 0.9989, what is the expected value of the insurance policy? Okay, we're going to set up another table because expected value tells us that I need to find the mean. So I'm going to set up a distribution table here. So X is going to be my net gain, and I'll have my P of X. And my two scenarios here are that the person that's purchasing the life insurance either lives or dies. So we need to figure out what their net gain is if they live or if they die. So going back and looking at our numbers here, let's just say if they live or if they die. So they're going to pay $245 for a 1-year life insurance policy. So if they live, then thankfully they're not going to collect on the life insurance, but they are going to have to have paid the $245. So they're actually going to be out the $245. So that's their net gain or loss if they were to live, is the premium for that insurance. Okay, let's say that they die, and unfortunately they're not able to collect, but their family would collect. The amount that they're going to collect is $180,000 minus the premium that they had to pay. So that's going to be, get these numbers right here, $179,755. That's going to be the net gain for the family if the 25-year-old does pass away and she's paid the premium here. So we're going to fill those numbers in here. So the net gain, if they live, they're going to be out the premium, which is negative 245. If she dies and the family collects on the insurance, they're going to collect 179,755 net, because they're still going to have to have paid the premium there. All right, on the probabilities, a 25-year-old woman is usually pretty healthy, so she has a really good probability that she's going to live through the year. So 0.9989 is going to be the probability that she lives through the year. So the probability that she dies is 1 minus the probability that she lives. So that probability is 0.0011. Okay, that's kind of the hard part. Now it just becomes the routine of finding the mean. So we're going to do X times P of X. Okay, so X is, if we multiply X times P of X for the first one, this is going to be negative 244.7305. We multiply it across here, we're going to have 197.305. And we know that to find the mean, we add these together, and when we add them together, we get negative 47. Okay, so basically what this is saying is that on average, the average person that has this type of insurance policy is going to lose about $47 per year with that. So by the same token, and this is important for answering some of the MyStatLab homework questions, while the person paying the premium is losing about $47 per year, the insurance company is actually profiting that $47 per year. So, so keep that in mind when you're answering those type questions, because there will be some like this on your homework. Also keep in mind that from an insurance standpoint, there are lots of different ways that that this can be adjusted. So if the insurance company is wanting to make more money off of them, then they could obviously charge more for the premiums. They could have larger insurance policies. If you're looking at this, you might have probabilities, you know, if someone's older, then this probability is going to be less, and that's going to affect it. So there's lots of different things that are going to affect this to cause this to be different. So, so just keep that in mind. If you have any questions on these, because I really do like these insurance problems, I think they're very practical and something that you should understand. But definitely reach out to me if you have any questions. Okay, and that takes us to the end of section 5.1.